Hey folks, today we're going to start out talking about physics. So in physics what we're trying to do is describe the world around us using math. We're going to start with motion, because once we understand motion then we can talk about why things move and stuff like that. But first we're going to talk about how things move. So when we're discussing motion's any change in an object's position. That's pretty obvious. You can't move unless you change where you're at, right? You can't not change where you're at and still be considered moving. That would be weird. So, when we talk about motion, we say that motion is relative to an observer's frame of reference. So, real quick, let's talk about what a frame of reference is. A frame of reference, or a reference frame, is the origin from where measurements are made. So if I set my pen here, and I ask you, is my pen moving? Well, the answer would be no, right? My pen's not changing its position relative to the camera. But that's because we chose the reference frame of the camera. If we talk about a different reference frame, like a reference frame far above the Earth, we would see the pen move from east to west as the Earth rotates around. So, breaking this down a little bit more, let's consider a train moving down the tracks at 10 meters per second. There's an observer on the train, an observer off the train, and then a person walking on the train. So, this person on the train would say, I see them move away from me at 2 meters per second because they're walking 2 meters per second. This person alongside the track would say, I see them move away from me at 12 meters per second because the train itself is moving 10. This person's walking an additional 2 meters per second on the train, so they would go away 12 meters each second. If this person changed direction and walked the other way, then instead of going 10 meters per second down, or 12 meters per second down the track, they'd be going 10 minus 2, so they'd only go 8 meters per second down the track. If the train was really, really long and there were no, like the train cars didn't have doors in between them or anything, and this person could run just as fast as the train was going, then if this person looked out the window, they wouldn't see trains or like trees or anything going by, right? This person would say, I see them not moving at all. And this person would say, they're moving, the opposite speed as the train's moving. So basically, in that situation, the train would act like a big treadmill, and this person would just be running there, and from the reference frame outside the train, wouldn't be moving anywhere at all. Inside the train's reference frame, they would be going towards the back of the train. So, there's two ways that we describe motion, or describe changes of position in physics. The first one, you should have heard of it before. It's called distance. Now, the thing about physics is, we take words that you've used tons of times, and we give them precise meanings. When we talk about distance, that's the total path length that an object travels. Symbol for distance is going to be a capital D, and we measure it in meters. The other one is called displacement. The displacement is a straight line length from the starting position to the final position. That's going to have a lowercase d as the symbol, and the units are going to be meters. So, real quick, one way that I like to illustrate that is if I start here, and I end here, but I take this path here is my distance, and then the straight line between the two, or the McQuiston straight line, is the displacement. I can't draw straight lines. Okay, so the displacement's from here to here, but the distance is going to be the total path length. So let's talk about this some more. So let's say we had a 10 meter square, and we wanted to go starting out from A to B. So if each side's 10 meters, and I go from here to here, what distance have I traveled? Well, distance would be 10 meters, right? Because each side's 10 meters. My displacement from beginning to end is the same. It would be 10 meters because I'm 10 meters from where I started out. Now, if I go from A to B to C, now my displacement would be 10 plus 10 is 20 meters. But oh my goodness, my kids. My displacement is going to be 14.1 meters. Now, I get 14.1 meters because there is more than, if each one of these blocks is 2, I've got a little bit more than 7. So the displacement would be 14.1 meters. If we go from A to B to C to D, now the distance is 30 meters, but how far are we from where we ended up? Only 10. It would just be this here. So it would be back to 10 meters. And if we go from A to B to C to D, now the distance is 40 meters, because we've gone the whole perimeter of the square, but the displacement is only going to be 0 meters, because we're right back where we started. So we didn't go anywhere according to the displacement. If you weren't paying attention and you missed the fact that it was moving, you turned away for a second because your kid was screaming, then you came back, you would say it didn't move at all. Now, distance always increases. So, since distance always increases, that means distance is always going to be greater than or equal to the displacement. If I travel in a straight line, it'll be equal to it. If I deviate at all from that straight line, the distance is always bigger.